This is a brief overview of important orogenic or mountain building processes with real-world examples given in a plate tectonic context. Here we see the south side of K2, the second highest mountain in the world. It's located in the Karakoram mountain range in Pakistan, which is part of a complex series of mountain ranges that include the Pamir, Hindu Kush, and Himalaya. Of the 5 highest mountains in the world, K2 is the deadliest. Approximately 1 person dies on the mountain for every 4 who reach the summit. First of all, we need to cover some basics about mountain building, orogenic basics. No, silly, different word. Orogeny does not equal orogeny. The word orogeny comes from the Greek mountain. The term was employed by the American geologist G.K. Gilbert in 1890 to describe the process of mountain building. You will see this term in different forms all throughout this course. For example, orogenic is an adjective that refers to mountain building. Orogeny is a noun referring to a mountain building event, like the Himalayan orogeny. Sometimes mountain ranges are referred to as orogen or orogenic belts. Now that we've cleared up any orogenic confusion, we can start talking about mountains. Major mountain belts or orogen are present all over the world, like the North American Cordillera, which includes the Sierra Madre of Mexico, the Rocky Mountains of the United States, and the Canadian Rockies. There's also the Appalachians, the Andes, the Alps, the Himalaya, etc. One important orogenic concept to understand is isostasy, or gravitational balance. This concept can be visualized by observing a set of wood blocks independently floating in water. Each block has a different thickness, and you'll notice that there's a relationship between the thickness of each block and how high it floats above the water. The thicker the block, the higher it floats above the water. You'll also notice that there's a relationship between the thickness of each block and how far it extends below the water. Again, the thicker the block, the lower it extends below the water. Now, if we cut off the top of the center block, it will respond by floating upward until it reaches some equilibrium position. These buoyancy relationships are governed by the overall density differences between the wood blocks and the water. Similar observations can be made about icebergs in the ocean. The thicker the ice, the higher it floats. Melt some ice off the top and the berg will rebound upward to a new equilibrium position. Well, these situations provide valuable insight into crust-mantle relationships. The crust, be it oceanic or continental, is less dense than the mantle. Thus, the crust is more buoyant and floats on top of the mantle. Furthermore, the thicker the crust, the higher it floats. Thus, elevation is related to crustal thickness. Thick crust yields high elevations, which form mountains. Thin crust yields low elevations, which form sedimentary basins. This is a color-coded map of crustal thickness, with the blue areas representing the thinnest crust, the green and yellow areas representing intermediate thickness, and orange and red being the thickest crust. Well, one takeaway from this is we find that the continental areas underlain by lower density continental crust are thicker than the oceanic areas underlain by higher density oceanic crust. The continental areas range anywhere from about 30 kilometers to maybe about 50 kilometers, with a few regions of higher crustal thickness. The average thickness of continental crust is about 35 kilometers. The oceanic areas you can see are consistently less than 10 kilometers or so in thickness, and the average thickness of oceanic crust is about 7 kilometers. Thus, we should expect areas of continental crust to have higher overall elevations than areas of oceanic crust. Indeed, crustal thicknesses correlate nicely with elevations, as shown by the elevations of the various continental masses and ocean basins. There are a few different ways to make mountains. One common way to do it is by thickening the crust with active tectonic compression at convergent plate boundaries. This may involve rapid oceanic plate subduction, island arc collisions, microcontinent, or even full-blown continental collisions. Another way to thicken the crust and make mountains is by magmatism. This may be related to volcanic arc magmatism at subduction zones, or isolated intraplate hotspot activity. A third way to make mountains involves mantle-related thermal uplift, typically found at mid-ocean ridges, rift zones, and intraplate hotspots. Think about this one for a second. We've been talking about thickening the crust and making mountains, but nowhere on Earth is the crust thinner than at a mid-ocean ridge. The answer to this conundrum is that the thermal effects from the underlying hot mantle asthenosphere buoy up the overlying oceanic crust, creating a mid-ocean ridge. Take away the heat, and there's no more ridge. This same thermal effect may occur above intraplate mantle plumes. All this talk of thickening the crust may make you wonder about the opposite, thinning the crust. Well, tensional tectonic stress resulting in extension of the crust will pull and stretch it horizontally and thin it vertically. This process may create mountains along the edge of the rift zone, like in the East Africa Rift or Rio Grande Rift, or even localized mountainous areas like the Basin and Range in the western U.S. But as rifting progresses, the crust eventually is stretched so thin and low that mantle melting occurs and oceanic crust starts to develop. This is how oceanic basins are initially formed. Another way to thin the crust is by erosion, which is relentless and always working to lower mountainous areas. But remember the iceberg example. As material is eroded off the top of the crust, the bottom of the crust will rebound vertically upward to compensate. This isostatic effect will prolong the mountain belt's lifetime, but eventually the effect will diminish and the mountains will be eroded flat, progressively exposing deeper and deeper crustal rocks at the surface. Mountains can form anywhere, but most typically they form at active plate tectonic boundaries. Let's review some of Earth's major mountain ranges in context of their plate tectonic environments. Let's start with the big enchiladas of tectonic collisions, the ones that occur at continent-continent convergent margins. The Himalaya are a mountain belt that formed at this type of plate boundary. This large tectonic mountain range is Cenozoic in age, formed from the subduction-related collision of the Indian plate beneath the Eurasian plate. The north-dipping subduction of the Indian plate more or less ended once the Indian subcontinent reached the subduction zone and collided with the Eurasian continent. This created the Himalayan mountain belt. The two plates are still in collision today. The great mountain Sagarmatha, otherwise known as Mount Everest, is the highest mountain peak on Earth, now estimated at 29,031 feet in height. Here is Mount Everest, or Sagarmatha, goddess of the sky, which is located on the Tibet-Nepal border. There are many ascent routes to the summit, with the Nepal routes and the North Face Tibetan routes being the most popular. As of 2019, over 300 people have died on Mount Everest. This is the popular Nepal route to the summit, ascending up the western Coombe, or glacial cirque, to the South Col, or saddle, which is on the southeast ridge, eventually heading to the summit. Now we'll swing over to the Tibet side. The geology of the mountain is dominated by metamorphic rocks. The base of the mountain includes very high-grade Neoproterozoic metamorphic rocks, like sillimanite-bearing gneiss, intruded by numerous granitic dikes and sills of tertiary age. The high-grade metamorphic rocks of the Neoproterozoic Rongbuk Formation include rocks like gneiss, schist, and marble. The overlying Cambrian North Col Formation consists of lower-grade schists, gneisses, and marbles, thought to have a deep marine origin. The conspicuous yellow band is an almost 600-foot thick layer that forms the uppermost part of this formation. A detachment fault separates the North Col Formation from the overlying Ordovician Camalanga Formation, which forms the upper 800 feet or so of the mountain. This unit consists of fossiliferous dolomite and siltstone deposited in a shallow marine environment. All of these rocks were deformed and metamorphosed largely during the Cenozoic Himalayan orogeny, involving the subduction and ultimate collision of the Indian plate with the Eurasian plate. Here are the north face climbing routes. This is the east face, or Kangshung face, of Mount Everest. And here is the ascent from the South Col, up the southeast ridge to the south summit, and ultimately the main summit, with a recently updated elevation of 29,031 feet. Much has been written about the climbing of Mount Everest. Any attempt to summit this mountain is fraught with a multitude of dangers, from the crossing of the Khumbu Icefall above base camp to the climb through the oxygen-deprived death zone. Much of this is chronicled in John Krakauer's book, Into Thin Air. Alternatively, the geology of the mountain itself is little publicized. Metamorphic rocks make up much of the mountain above Camp 3, with limestone or marble forming the distinctive yellow band farther up. The very top of the mountain is formed of Ordovician limestone. This sedimentary rock was originally deposited in a shallow ocean almost 500 million years ago, and is now at the highest point above sea level. Think about that for a second. While the mountains of the high Himalaya are relatively young, Cenozoic, the rocks of which it is composed are relatively old, early Paleozoic and older. These older rocks underlie Dhaulagiri, shown on the right of this image in cross-section. The Himalayan mountain belt is a complex collection of tectonic terrains, each bounded by major thrust faults. These terrains are located between the Indian lowlands to the south and the high Tibetan plateau to the north. At 28,251 feet, K2 is the world's second highest peak, located to the west of Mount Everest, and as of June 2018, only 367 people had completed the ascent to its summit, while there have been 91 deaths during attempted climbs. K2 is part of the Karakoram Range and straddles the border between Pakistan and China. Its more northerly location makes it susceptible to cold and inclement weather. K2 has a number of ascent routes, but is the only 8,000 meter plus peak never climbed from its eastern face. K2 is the second highest peak in the world, with a summit elevation of 28,251 feet. Its north face is also worthy of recognition, as it has a height of around 3,600 meters, or about 11,800 feet, making it quite possibly the highest cliff face in the world. K2 is largely composed of the K2 gneiss, which ranges in age from 115 to 120 million years old. And the gneiss is intruded by dikes with a variety of compositions. The gneiss likely had a granitic protolith that was metamorphosed during the initial phases of the collision between India and Eurasia. The Appalachian Mountains of eastern North America are a largely tectonic mountain range that formed during the Paleozoic era. At least 3 separate orogenic events occurred during that time. The tectonic orogeny resulted from an island arc collision during the later part of the Ordovician period. The subsequent Akkadian orogeny was due to a collision with the microcontinental fragment Avalonia during the Devonian. And finally, the Alleghanian orogeny occurred during the latest Mississippian, Pennsylvanian, and Permian periods, and involved the collision of Laurentia, Proto-North America essentially, with Gondwana, the great mass of southern continents that included South America, Africa, and others, to ultimately form the supercontinent Pangaea. The Appalachian Mountains and related areas stretch from Mississippi all the way to New England. This region contains several different landscape provinces, each with its own distinctive geology. For instance, the Piedmont province is a low-relief plain to the east of the mountains and is made up of Paleozoic and older igneous and metamorphic rocks. Some of this province is actually covered by younger sedimentary rocks farther east. The Allegheny Plateau province forms the western margin of the mountain belt and is composed of gently deformed to flat-lying Paleozoic sedimentary strata. The Valley and Ridge province lies in between the other two and represents a fold and thrust belt of Paleozoic and older rocks. Like a tectonically crumpled crustal rug, notice the alignment of the folded mountains. This is a big clue to the relative direction of the compressional forces involved in the Alleghanian orogeny, over 300 million years ago. This area includes a multitude of Paleozoic geologic structures, including anticlines, synclines, reverse faults, thrust faults, etc. Well-defined plunging folds form many of the ridges and valleys in this region, like at Massanutten Mountain, Virginia. Although no longer actively forming, these mountains were once a magnificent orogenic belt, straddling Pangaea's equatorial area. And they are still a worthy hike today, even after hundreds of millions of years. Let's visit the Massanutten Mountain area of Northern Virginia. Massanutten Mountain and related northeast trending ridges are part of Virginia's Valley and Ridge physiographic province and stretch from just east of Harrisonburg northeastward towards Strasburg and just west of Front Royal. Here, early Paleozoic sedimentary rocks have been compressed into a series of northeast trending folds. Differential erosion has created valleys underlain by limestones and shales. Resistant units like sandstone form the prominent ridges. The arcuate outcrop pattern belies the nature of these ridges as plunging folds. Shales of the late Ordovician Martinsburg Formation form the lowlands adjacent to the mountain, whereas the resistant early Silurian Massanutten sandstone forms the bold ridges. The axial valley is underlain by various shale-dominated units, like the Marcellus Shale and Mahantango Formation. These folded mountains are part of the Massanutten synclinorium, a large downfold where the limbs dip mostly toward a central fold axis, with smaller synclines and anticlines superimposed on it. These plunging folds formed during the late Paleozoic Alleghanian orogeny, which involved the collision of Euramerica, or Proto-North America, and Gondwana, which included Proto-South America, Africa, and other continental masses. This collision resulted in the final assembly of the supercontinent Pangaea. Turning to the southwest, we follow Massanutten Mountain back toward Newmarket Gap. Ocean-continent convergent margins are typically composed of iconic stratovolcanoes that form large continental volcanic arcs. A classic example of an ocean-continent convergent mountain range, the Andes Mountains in South America. These mountains extend along the western side of the continent and are an excellent example of a tectonic volcanic mountain belt. These mountains began forming in the Cretaceous period and continue to this day. The Andes formed as a result of the eastward subduction of the Nazca Oceanic Plate beneath the continental portion of the South American Plate. Subduction-related tectonism and volcanism are abundant all along this plate boundary. Numerous high-magnitude earthquakes occur along the subduction zone, and the Andes continental volcanic arc is dominated by a great many active stratovolcanoes, located in several volcanic zones along the length of the mountain belt. These mountains cast a significant rain shadow, helping to form the Atacama Desert in the north and the Patagonian Desert in the south. A few iconic locations include Alpamayo, one of the most conspicuous peaks in the Cordillera Blanca of the Peruvian Andes, and of course, Machu Picchu, the famous 15th century Inca citadel. Machu Picchu is located in the central Peruvian Andes at an elevation of about 8,000 feet. During the Eocene, subduction-related convergent tectonics uplifted the area to its high elevations. Machu Picchu, or Old Peak in Quechua, is actually the mountain along the ridge to the south of the citadel, and Huayna Picchu, or Young Peak, is the mountain to the north, and Huayna Picchu is the one you typically see in pictures. The Machu Picchu Ridge is located within a small northeast trending graben, and the ridge itself is composed of mostly granite and lesser granodiorite, with mafic intrusions locally present. The Machu Picchu Pluton is Triassic in age, 246 million years old, and is related to the larger Quillabamba granite complex. The stone used in constructing Machu Picchu was quarried from two large deposits of fractured granitic blocks located near the Sacred Plaza. Indeed, the availability of building stone in such a rugged area may have been one reason why the Incas selected this location to build their citadel. That and the nearby springs. There's the high peak Solcantai, and the Peruvian Andes. Looking south, where the mighty Andes rise above the rainforest of the Amazon basin and the blue waters of the Pacific Ocean. The Cascade Mountains are a largely volcanic mountain range of Cenozoic age located in western North America. This continental volcanic arc formed from the subduction of the Juan de Fuca and Gorda oceanic plates beneath the continental portion of the North American plate. Numerous high-magnitude earthquakes occur all along the subduction zone. The volcanic arc extends from northern California northward into Oregon and Washington, and ultimately British Columbia. The Cascades are large enough to create a rain shadow effect across the eastern portions of Washington and Oregon. The dominant volcano type in the Cascades is the stratovolcano, like Mount Rainier near Seattle, Washington. However, the Cascades include a variety of other volcano types, including calderas, lava domes, shield volcanoes, etc. The Cascade Range is a large, north-south trending continental volcanic arc, extending from British Columbia in Canada down through Washington and Oregon into Northern California. The Cascades include a variety of volcano types, with iconic snow-capped stratovolcanoes being the most prominent. What qualifies as an active volcano is subjective, but essentially it's one that has erupted lava or tephra in the last few decades, is currently erupting, or is expected to erupt very soon. Most of the Cascade stratovolcanoes can be considered dormant, as they are still capable of erupting, just haven't in a very long time. Most Cascade volcanoes have long eruption histories, with alternating periods of dormancy and eruptive activity. Shown here is the eruption history for Mount St. Helens over the last 23,000 years. And even in dormancy, many of the volcanoes commonly produce relatively minor phreatic or steam blast activity and lahars, or volcanic-related mudflows. Let's take a quick tour of some of the major volcanic centers of the Cascade Range. If you've ever been to the Seattle area, I'm sure you've seen Mount Rainier. Rainier is the highest mountain in the Cascades at 14,417 feet. The present highly glacially eroded cone has grown over the last 500,000 years or so, with the last major lava and or tephra-producing eruption occurring about 1,000 years ago. Looking north from Rainier, we can see Mount Baker near the Canadian border. The last major magma-related eruption at Mount Baker occurred roughly 6,700 years ago, although it has had a period of recent phreatic activity. And then off to the northeast, there's Glacier Peak, among others. The last major eruption of Glacier Peak was around 1,100 years ago. As we turn south, we're going to see a number of other major volcanoes. To the southwest, we'll first come across Mount St. Helens. Mount St. Helens has been an active volcano on and off for the last 300,000 years or so, with May 1980 being the latest eruption. Lava dome growth has occurred since, from 1980 to 1988, and from 2004 to 2008. And just to the east of Mount St. Helens is Mount Adams. This volcano consists of several overlapping stratocones, with the last major eruption about 1,000 years ago. Moving south into Oregon, we next come to Mount Hood. Mount Hood is home to 12 glaciers and snowfields and is the highest point in Oregon at 11,249 feet. Mount Hood's last significant eruptive activity was about 200 years ago. Here is Mount Jefferson, which last erupted 6,500 years ago, but has not erupted in historic time. As we continue south, here are three sisters. Faith, the north sister, is a shield volcano and the oldest of the trio. Hope is the middle sister, a basaltic stratovolcano. And Charity is the south sister, a rhyolitic stratovolcano that last erupted about 2,000 years ago. And to the southeast is a slightly different volcanic center. This is Newberry Volcano, more of a shield volcano punctuated by calderas and lava domes. Not like your typical Cascade Range stratovolcano. We now move southwest. Here, of course, is Crater Lake, the site of the former stratovolcano, Mount Mazama. The catastrophic eruption of Mount Mazama and subsequent caldera collapse occurred 7,700 years ago. The area is largely covered by felsic tuff and related volcanics, not to mention two intracaldera andesitic scoria cones, Wizard Island, which is above water, and Miriam Cone, which is below water. Now into California, where Mount Shasta is a composite of four andesitic cones, including the well-defined Shastina, and numerous related cinder cones and lava domes. The last major eruptions here occurred about 3,200 years ago. And the southernmost of the Cascade volcanoes is Lassen Peak. The youngest volcanic structure is a 2,000-foot-high rhyodacite lava dome, one of the largest in the world. After over 25,000 years of dormancy, Lassen erupted in 1914, with a major eruption occurring in 1915. Smaller steam blast or phreatic eruptions occurred until 1921, and this was the last eruptive activity in the Cascades until the 1980 eruption of Mount St. Helens. Let's zoom out and look at the Cascade Range in a broader plate tectonic context. The modern-day Rocky Mountains are a complex tectonic volcanic mountain range formed from the latest Cretaceous to the early Paleogene, about 80 million to 40 million years ago. They were formed during the low-angle subduction of the Farallon Oceanic Plate beneath the continental portion of the North American Plate. This mountain-building event is known as the Laramide orogeny. The Rocky Mountains extend from Mexico, where they are called the Sierra Madre, into the U.S., and then into western Canada, where they're the Canadian Rockies. In the U.S., the Rockies can be subdivided into southern, middle, and northern areas, each having a slightly different deformational signature. Iconic landforms representing the geology of the southern Rockies in Colorado are the flatirons, formed along the eastern flank of the Front Range, exposed between Colorado Springs and Fort Collins. In the Boulder area, here we see the campus of the University of Colorado, Boulder. In the area to the west, along the Front Range, several prominent flatirons are located on Green Mountain. From the north, the first ones are creatively named the first, second, third, fourth, and fifth flatirons. These east-dipping layers are composed mainly of arkose and conglomeratic sandstone of the Pennsylvanian Fountain Formation and quartz aaronites of the Middle Permian Lion Sandstone. These flatiron units overlie the much older intrusive rocks of the Paleoproterozoic Boulder Creek granodiorite pluton. Let's move south towards El Dorado Canyon. Other green mountain flatirons include Hillbilly, Hippohead, Unicorn, Willie B., Satan Slab, and others. To the south on Boulder Mountain, there's Devil's Thumb, Fiddlehead, the Seal, Tower of the Moon, and the Fat Iron, just to name a few. These rocks were originally tilted as part of a series of large basement chord uplifts formed during the Laramide orogeny that occurred roughly 80 million to 40 million years ago. Subsequent stream erosion has cut into the tilted layers, creating the flatirons. Ocean-ocean convergent margins include many examples of island arc mountains. The Aleutian Islands are a Cenozoic island arc formed from the subduction of the Pacific Oceanic Plate beneath the oceanic portion of the North American Plate. The Aleutians form most of the tail of Alaska and include many active stratovolcanoes, like those in the islands of the Four Mountains. The islands of the Four Mountains group in the Aleutian Arc include several volcanic islands. It's not just four. These include, from the southwest, Amukta, Chagulak, Unasca, Herbert, Carlisle, Chuginadak, Cagamil, and Uliaga. We'll start at the southwest end. This is Amukta Island, stratovolcano and summit crater, last active in 1997. The smaller nearby stratocone of Chagulak has no known recorded eruption history. We move to the east and find the island of Unasca, with the older stratovolcanoes to the west, and a shield volcano with calderas occupying the eastern part of the island, and last active in 1937. Then we come to the three main islands of the island group: Herbert, Carlisle, and Chuginadak. Herbert is a stratovolcano with a nice wide summit crater with no known eruptive activity. Farther north is the beautifully symmetrical cone of the Carlisle stratovolcano, most recently active in 1987. And then the larger island of Chuginadak includes a southeastern island with a volcano named Tana. But the main attraction here is Mount Cleveland, one of the most active volcanoes in the Aleutian Arc. And the last two islands of the island group include Cagumel, with its two volcanic cones, last active in 1929, and then Uliaga, which has no known eruptive record. These are the islands of the four mountains. Let's zoom out and look at the broader plate tectonic context. Oceanic divergent margins are exclusively composed of submarine mountains and ridges. The Mid-Atlantic Ridge is a thermal volcanic mountain range formed along the oceanic divergent margin in the Atlantic Ocean basin. In the North Atlantic, it separates the oceanic portion of the North American plate from the oceanic portions of the Eurasian and African plates. In the South Atlantic, it separates the oceanic portion of the South American plate from the oceanic portion of the African plate. The Mid-Atlantic Ridge was originally formed during the rifting and breakup of Pangaea in the Triassic period, and continues to form today. It is a relatively slow-spreading ridge, roughly 2.5 centimeters per year, and at roughly 16,000 kilometers in length, the only portion that is above sea level is at Iceland. Continental divergent margins include mostly rift-related mountain ranges. The Basin and Range is actually a wide continental rift that includes many isolated mountain ranges. It extends from northern Mexico into New Mexico and Arizona, then up into California, Utah, and Nevada. The Basin and Range in southern Arizona includes many relatively small mountain ranges. This province began forming as early as 30 million years ago and continues to spread to this day in Nevada and California. Early rapid spreading formed low-angle normal faults, or detachment faults, and metamorphic core complexes in some areas. Extensional deformation eventually slowed and created block fault mountains and graben that formed along high-angle normal faults. The Sierra Estrella Mountains, southwest of Phoenix, are an example of a Basin and Range fault block mountain. Let's look at the Basin and Range landscape of southern Arizona, starting above the Safford Basin in southeastern Arizona. Heading west, the first range we'll cross is the Pinaleño Mountains. Mount Graham has an elevation of 10,724 feet and is the highest point in the Arizona Basin and Range. It's also home to the Mount Graham International Observatory with the Large Binocular Telescope, one of the largest optical telescopes in the world. We continue west across the Aravaipa Valley and the Galliero Mountains. And then over the San Pedro Valley and the mighty Santa Catalina Mountains. With Mount Lemmon being the high point. Then there's the Tucson Basin and the Tucson Mountains on the western side. The Avra Valley and the smaller eroded Ross Scrooge Mountains to the west. Of note are the Babakivri Mountains to the southwest, which are home to Kitt Peak and the Kitt Peak National Observatory, which has the largest solar telescope in the world. The Sierra Nevada are a tectonic mountain range in California that formed along the western margin of the Basin and Range continental rift. It is essentially a large tilt block that formed around 10 million years ago, but recent studies indicate that the Sierras may have started to form as early as 40 million years ago. The Sierras include Mount Whitney, the highest point in the lower 48 U.S. states, at 14,505 feet. Mount Whitney is located in the southeastern Sierra Nevada. The rocks of the Mount Whitney area belong to the late Cretaceous Whitney intrusive suite and placed from 87 to 80.4 million years ago, and correspond to the latter part of the Plutonism that occurred in the Sierra Nevada batholith. The Sierra Nevada frontal fault zone dips 60 to 80 degrees east, with about 3 kilometers of down to the east displacement. The 83 million year old Whitney granodiorite forms most of the area around Mount Whitney. This unit is porphyritic, with potassium feldspar phenocrysts as large as 4 to 8 centimeters in size. Granite porphyry sills and dikes are also common around the summit. As we pan around Mount Whitney, we see the upper western slopes of the Sierras, which are entirely within Sequoia National Park. Mount Whitney stands sentinel at the edge of the Sierras, high above the western margin of the Basin and Range province. The Owens Valley area here includes the Alabama Hills near Lone Pine, Owens Lake, more up Playa really, and the Inyo Mountains on the far side. The glacially sculpted landscape includes numerous U-shaped valleys, knife-like ridges or arêtes, bowl-shaped cirques and cirque lakes, known as tarn, with glacial till and rock glaciers locally present. For instance, Mount Hale forms a glacial horn, with a rock glacier and the Wales Lake Tarn filling the adjacent cirque. The small lakes formed along Whitney Creek are called Paternoster Lakes, as they resemble beads on a rosary. Here's the steep eastern face of Mount Whitney. At 14,505 feet, the highest point in the lower 48 United States. It's also the terminus of the John Muir Trail, which is 213 miles in length and passes through Yosemite, Kings Canyon, and Sequoia National Parks. Intraplate hotspots include numerous volcanic mountains that form both in the oceans and on continents. The Hawaiian Islands and Emperor Seamounts together represent a continuous line of volcanic islands and submerged volcanic mountains, known as Seamounts, in the Pacific Ocean. The Emperor Seamounts began to form in the latest Cretaceous period, above a mantle plume. With movement of the Pacific Plate over this mantle plume, additional volcanic islands formed, with the older volcanic islands eventually subsiding beneath sea level. The latest of these volcanic islands are the present-day Hawaiian Islands, from Kauai to the Big Island of Hawaii, and all are less than 6 million years old. Large shield volcanoes form most of these islands. 5 shield volcanoes form the Big Island of Hawaii, including Mauna Kea, the highest point in the Hawaiian island chain at 13,802 feet above sea level. But Mauna Loa is the largest single mountain on Earth, rising about 30,000 feet from its base on the seafloor to its summit. Mauna Kea is located just to the northeast of Mauna Loa. Mauna Kea is about 1 million years old and last erupted between 4,000 and 6,000 years ago, making it a dormant volcano. And this large shield volcano has numerous satellite cinder cones that dot its flanks. Mauna Kea's 13,803 feet summit elevation makes it the second highest island peak on Earth. This and several other reasons make Mauna Kea an ideal location for astronomical observation. The Mauna Kea observatories include several large telescopes, like the 8.1 meter Gemini telescope, the 8.2 meter Subaru telescope, and the mighty 10 meter Keck binocular telescopes. Well, that's all for now. Till next time.